So if we're looking at fields, there's two field laws that we need to consider. One is Newton's universal law of gravitation, which says that every particle attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between their centers. What's important is if I were to, for example, have planet Earth and I stuck a satellite out there, you would need to consider the distance from the center of the Earth to the center of the satellite, which means that you often need to add this distance, which let's say is 6 times 10 to the 24 kilogram, at least meters. I really don't know what it is, but you'd have to add that and that together to get the distance between their centers. So you always need to be very aware of that. You can work out the gravitational acceleration on any planet by saying what is the mass of the planet, substituting into g m planet divided by the radius of the planet squared. Remember that in this case, g is 6,67 times 10 to the negative 11 with some ugly unit. This information is all provided on the information sheet. So learn how to write that down using this as a tool. The same thing is true with Coulomb's law, where two charged objects will exert a force on each other that is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. And in this case, k is 9 times 10 to the power of 9 with some very ugly unit after that. Need to know about electric fields. Electric fields are a region of space where an electric charge will experience a force. Officially, it is in the direction that a positive point charge would move. Well, where would a positive point charge move? Positive would move towards negative. So it's positive to negative. You need to know the shapes of all of these different fields. So if I had a positive point charge, I would be able to say that all of those, it radiates out and it is away from positive towards negative. Let's say these were both negative, then you would be able to say that you land up with this void in the middle over here because these counteract each other, away from negative towards positive, and even if the positive doesn't exist, it's away from the negative, and obviously the same shape, but the arrows would be in the different direction if these were two positive point charges. If it was a positive and a negative point charge, then you'll find that they'll actually connect with each other and you'll get attraction in between the two, and it's away from the negative and towards the positive, away from the negative towards the positive. If you had a hollow sphere, it would just be a big point charge. So it's towards negative, and it looks like the sun again. What about if I'm asked to draw the field between parallel plates? It is a uniform field, which means that these lines need to be evenly spaced apart, and at the ends there need to be little curves, again from the positive to the negative. You may be asked to do calculations on electric field strength or force. In each case, you land up having to substitute in whatever information they've given you. Make sure you're in newtons, make sure you're in coulombs. Sometimes you get nanocoulombs, and if it's nanocoulombs, it's times 10 to the negative 9. If it's microcoulombs, it's times 10 to the negative 6. So you need to be aware of the number of coulombs. And then remember also they like to ask questions where they stuff you around in terms of the distance between the objects. They give you that R in centimeters, let's say 30 centimeters, which is 0,3 meters. Or they say 30 millimeters, and then you need to convert it into 0,03 meters. So you need to be aware of your units in both of these. This K value is again just the 9 times 10 to the power of 9 because it's all got to do with electric fields and electric field strength and Coulomb's law. You are expected, according to the curriculum, to be able to work out a resultant force. So let's just take this object over here at P, and we can say that this is 5 nanocoulombs and this is 3 nanocoulombs, and let's say that P is, that there's 40 millimeters between them, and P is 10 millimeters from the 3 nanocoulomb charge. They say, what is the resultant electric field? Because an electric field is a vector. What is the resultant electric field at point P? What are we going to do? first thing is, what is the electric field as a result of just the 3 nanocoulomb charge? So I can say electric field strength is equal to kq over r squared, and that is 9 times 10 to the power of 9, 3 times 10 to the power of negative 9, and 0,01 squared, because I had to convert that 10 millimeters into meters. I get an electric field strength of 2,7 times 10 to the power of 5 newtons per coulomb. This is a positive charge, so it is going to be away from positive, so it's towards the right, away from the positive. Taking a look at the second one, we land up with electric field strength is equal to 9 times 10 to the 9, 5 times 10 to the negative 9. Distance is now the remaining 30 millimeters, and that's 0,03 squared, and I land up with 5 times 10 to the 4 newtons per coulomb, and again it has to be away from the positive, so it's going to be right. Now at this point I've got one force pushing in that direction, and I have another force pushing in that direction. They're 2,7 and times 10 to the 5 and 5 times 10 to the power of 4. So how am I going to get the resultant electric field? I'm going to go big minus small, so it's going to be 2,7 times 10 to the power of 5 minus 5 times 10 to the power of 4, and I get an answer of 2,2 times 10 to the power of 5. And which one's winning? The one actually towards the right. Sorry, this is not to the right. This is away from the positive. It's to the left. So the winner is to the right.